Hello from Mexico, and it's very glad for me to stay with you at the International Congress of Apollonia University. So I would like to thank Professor Leonard Athanase for his kind invitation. Now, let me share with you the PowerPoint presentation. Wait a minute, please. Well, the title of this talk is Development of Polymer Nanoparticles Stabilized with a PBA phthalate Mixture and Their Potential Use for the Targeted Delivery of Antitumor Agents. As you can infer from the title, this is an interdisciplinary research. So it's the product of a collaboration with my colleagues of the biomedical field. In Mexico, Roberto Olvera-Guillen, Gabriela Rocha Botello, Marta Cruz Soto from the University of the Mexico Valley, UVM, and also a collaboration with Carla Oyuki Juarez Moreno from the National Autonomous University of Mexico, the same university where I work. Yes, although she works at a different research center, which is located in the north part of Mexico, very close to the border with the United States. Well, the outline of this talk. For instance, I'm going to briefly talk with you about the conceptual design of the nanocarrier, and then I will show you some equipment used in the experimental section of the work, and then I will emphasize on the results and their discussion. I will spend more time on this. Finally, I will show you the conclusions and perspectives. Well, drugs used in chemotherapy affect both healthy and cancerous cells. This is the drugs for chemotherapy do not distinguish between healthy and cancerous cells. So they lead to undesirable, to the well-known undesirable side effects, as the ones I show here with these pictures. Then an alternative is to use nanoparticles as drug carriers with the ability to preferentially act on tumors and on tumor cells. The final idea is to inject this the colloidal mixture by an intravenous way to the human body. This is a cartoon where I try to schematically represent the composition as well as the structure and particle size of the nanocarrier. Let me justify why we use each one of these components. Let's start with the polyvinyl acetate. This is a hydrophobic, biocompatible, and biodegradable polymer that we synthesize in this work by using the emulsion polymerization technique, which is a kind of free radical polymerization, using vinyl acetate as monomer, which is a very, very cheap monomer available in Mexico and in many parts of the world. And eugenol that I suppose you are familiar with. This because it is used in dentistry. It has application in dentistry. Eugenol is a hydrophobic oil, and it is a good solvent for polyvinyl acetate. Thus, this mixture forms a gel. We don't have a a solid core, solid particles, but they are a gel instead. It has been reported that eugenol induces apoptosis and can inhibit metastasis of breast cancer cells as well. So this is why we choose eugenol. This component is a very cheap material compared to other anti-tumor drugs or anti-tumor agents. For example, paclitaxel is 10 to the 5 times more expensive than eugenol. Now, PBA, this polyvinyl alcohol, that in reality is a copolymer of polyvinyl acetate and vinyl alcohol, because it is produced by partial hydrolysis of polyvinyl acetate. So we have a random distribution of these hydrophobic and hydrophilic units. Because of the amphiphilic nature of PPA, it is used as a colloidal stabilizer. And it is a biocompatible and biodegradable polymer, which is a request for for this kind of application. And an important feature of PBA is that it provides protection against the mononuclear phagocytic system. And also, PBA is grafted to the polyvinyl acetate chain during the emulsion polymerization reaction. This is important because otherwise, when nanoparticles are diluted, for example, during the in vitro test, PBA can dissolve back to the continuous medium, and then coagulation between particles can occur, and this is not desirable. Another possibility is that when it's injected to the bloodstream, it implies dilution as well. So we need to keep the colloidal stability of our nanocarrier. Now, folate. Folate allows the receptor-mediated internalization and imparts specificity. This is because cancer cells overexpress the folate receptors. Therefore, if our nanocarrier has folate molecules, it is expected that it will attach preferentially to the cancer cells rather than the healthy cells. And in this way, it is expected to obtain the desired specificity. Now, particle size, that's an important characteristic as well. For limitation of time, I can explain how we get to this number. But what I can tell you is that it's very well justified that particles must have this particle size in this range, 50 minus plus 20 nanometers. This is a recommendation from the literature, and we can deduce from all the reports obtained in the literature. Wow. These are the equipments, the main equipments we used in this research. This is a computer controlled reactor where the emulsion polymerization were performed. This is a dynamic light scattering apparatus for particle sizing, a Dunoid tensiometer for interfacial tension measurements. And this is a high-resolution scanning electron microscope. This is a flow cytometer, which was used to quantify the cell death by apoptosis and necrosis. We use two PBAs of different molecular weights. PBA 1, which molecular weight is from 13,000 to 23,000. This is the lower molecular weight. And the other one, PBA 3, is nearly an order of magnitude greater, the molecular weight. So part of the research of the was to choose or to determine which of these stabilizers, which of these molecular weights is more convenient for the synthesis of our nanoparticles. So next, I'm going to show you what we did in order to determine which PBA is more convenient. Here I show the evolution of the number of particles as a function of monomer conversion and the corresponding evolution of the particle diameter. This colored area represent the target range particle size. And 50 is the average. This is the target, the average particle size. As we can observe in this plot, at early times of the polymerization, there is a drop of the number of particles, which implies limited coagulation, which leads to a sudden increase of the particle size, which is greater or that is above the desired size range. Then we made several experiments, and always we had this this problem of coagulation. So we tried to find out what was the problem. And for this purpose, we made interfacial tension measurements using both PBAs. And what we found is that with the PBA of higher molecular weight, the interfacial tension was higher compared to the interfacial tension obtained with the PBA of low molecular weight. This is high molecular weight is less efficient to reduce the interfacial tension. This can be explained with these cartoons. One thing is that the hydrophobic segments in the PBA chain are mainly on the core of the chains, and only a small number of hydrophobic chains are in the periphery. And then there are a few points for contact with the substrate, with the interface. And in contrast, with the lower molecular weight, the hydrophobic segment represented by the green circles, it is more available than with the higher molecular weight. It's more available on the periphery, so there are more absorption points available, and therefore PBA1 has a higher capacity or efficiency to lower the interfacial tension. Then another phenomena that has to be taken into account is that bridging flocculation can be occurring. This happens when the size of the stabilizer is greater than the size of the particles that are supposed to be stabilized. then flocculation occurs instead of repulsion. Then what we need is that the size of the stabilizer must be smaller than the size of the particles we want to stabilize. Therefore, we use the PBA with the lower molecular weight, PBA 1. Well, that's what we did. We again made a scan of reaction conditions. We studied the effect of the initial surfactant monomer and initiator concentration, and we found that at this condition we obtained the desired or the target particle size. We couldn't avoid at all limited coagulation, as we can see here. This is for the selected reaction conditions. However, the limited coagulations give us some beneficial aspects in certain way, because it leads to narrower particle size distribution. For example, here we try to represent a broad particle size distribution, and then when limited coagulation occurs, it is inherent homogenization of particles, so the size distribution becomes narrower, which is desirable characteristic for the nanocarriers for this kind of application. This is how our nanocarriers looks like in high resolution scanning electron microscopy. And these are particle size distribution as measured by dynamic light scattering. Here we show the distribution of 5 runs, experimental runs. So we have a very good or a nice reproducibility. Now, what about the functionalization? Usually, functionalization is made by making laborious chemical reactions and purifications in order to form a chemical bond between the ligand and the drug, and sometimes with a spacer. However, what we propose is to perform this functionalization by means of a physical way. This is physical functionalization instead of chemical functionalization. How we did this? Well, this idea was inspired in the work by Ramirez and collaborators from our group in Mexico. What he did was to measure the interfacial tension as a function of PBA concentration, and then stop adding PBA at 5 grams per liter of PBA, and then start to add sodium iodosyl sulfate. And what we observed is that interfacial tension, instead of still decreasing, it increases. And this is because SDS molecules started to associate or to form a complex with PBA, and then the conformation of the chain of the PBA chains changes. It becomes more stretched, and this implies that some hydrophobic segments that absorb an interface desorb back, and this causes the increase in the interfacial tension. So what we did was to test if folate behaves similar to SDS. This is, we want to test if folate can form a complex with PPA. And then what we found is that that indeed folate behaves similar to SDS from a complex as it is deduced from these interfacial tension measurements. This is the chemical structure of folate, and we have a hydrophobic part and then a hydrophilic part. This is an amphiphilic molecule. However, because of the bulky and planar shape of the structure, folate by itself does not absorb at the interface, but only forms a complex with PPA. So we can have this this scenario, the same as than SDS. Now, in order to obtain more evidence about the complex formation within PPA and folate, what we did was to measure the size of PPA pseudomicelles in the presence and absence of folate. And then in the presence of folate, we have a bigger micellar size than in the absence of folate. Then, in order to functionalize our nanocarrier, we simply add folate to the colloidal mixture. And what we used was the mass ratio present, or that corresponds to the maximum and the interfacial tension measurements. And that it is really a very simple method. But now the question is, this physical functionalization works in vitro test. Is it possible that it can allows endocytosis? Before I show you the biological test, let me show you the set of potential results. This is the nanocarrier without folate, without functionalization, and after functionalization. As we can see, there's a significant increase in set of potential, which confirms the presence of folate, or the formation of this complex between PPA and folate. Here I show you the biological test. This is the cell death by apoptosis and necrosis as determined by flow cytometry. We use 5 kinds of particles. The nanocarrier itself. This is the polymer stabilized with PPA. This is the same, but with addition of folate. And this one does not have a folate, but it was loaded with eugenol. And these particles is the complete nanocarrier, loaded with eugenol and physically functionalized with folate. As we can see in these plots, this is in the absence of eugenol. There is no cell death. So that was good news because the nanocarrier is not cytotoxic. When eugenol was used alone, we obtained we detect cell death by late apoptosis and early apoptosis, the red ones, the red one part and the green part is late apoptosis. Well, this result was expected. And also with the nanocarrier loaded with eugenol, it exhibits cell death as well. The interesting thing is that when the particle, when we use the particle, the functionalized particle loaded with eugenol, cell death increases compared with the same concentration used in the runs, in the experiments without folate. For example, compare 1 microgram per milliliter with 1 microgram per milliliter in this experiment. This is significantly higher than this one. In here, 10 micrograms per milliliter, we obtain almost 75 cell death by a combination of late and early apoptosis, which is much higher than the correspondent obtained in these experiments. Therefore, the presence of folate it's very important. It highlight the importance of the presence of folate, and that internalization is performed by in a receptor-mediated way. Finally, the conclusion and the future work. Emulsion polymerization is a suitable method to synthesizing polymer nanoparticles to be used as nanocarriers. And PBA with the lowest molecular weight exhibited the best performance due to its better stabilizing capacity compared to the PBA with highest molecular weight. Cell viability was markedly affected by our functionalized nanocarrier, which supports the notion that folate is present on the particle surface and is uptaken by the cells through a receptor-mediated endocytosis. Polyvinyl acetate nanoparticles covered with the aforementioned supramolecular structure are promising nanocarriers for the targeted delivery of eugenol as an anti-cancer agent for future testing in vivo cancer models. Then I just want to thank some institutions that support this research. And these are my colleagues. These are the students, Gabriela and Roberto. These are my colleagues, Carla Juarez, Marta Cruz Soto. Thank you very much for your attention. Just let me show you how far we are from Romania. We are about 11,000 kilometers from each other here, and then we are to the south of the United States. And these are some aspects of the National Autonomous University. Here were performed the Olympic Games in 1968. This is the main campus of the university. And where I work, this small campus at Juriquilla, but it's also a nice place. You're very welcome to visit us. Thank you. Thank you very much for your kind attention and again for the invitation.